Okay, so this last one on moments, 5.4. It says you can solve problems about non-uniform bodies by finding or using the centre of mass. So the mass of a non-uniform rigid body can be modelled as acting at its centre of mass. So if a rigid body is not uniform, then you will either be told where the centre of mass lies or you will be asked to find where it is. So a couple of examples here. Example 10. Sam and Tamsin are sitting on a non-uniform plank AB of mass 25 kilograms and length 4 meters. The plank is pivoted at M, the midpoint of AB. The center of mass of AB is at C, where AC is 1.8 meters. Sam has 35 kilograms to block. Right, so I'm just going to do a quick sketch of this. So there's the plank AB, and that's sitting right at the center. That is M. In fact, I'm going to put a thing like that, M. You got Sam is sitting at A. Sam and Tasman has 25 kilograms and sits at A. So Sam has 35 kilograms. Tamsin sitting here. Sorry, get right in a bit. Right, so there we got Tamsin has 25 kilograms, sits at A, so that's 25 G to make it a weight. We've got the centre of mass of the plank is over here, and the plank is 4 meters long, it's 25, so that's 25 G to make it a weight. That is 1.8, therefore that is 0.2. Where must Sam sit on the plank? So I'm going to put him somewhere here, and he has got a mass of 35 kilograms, which means it is 35 G. Where must Sam sit on the plank to make it so it remains horizontal, so it's in equilibrium, as it were? So it doesn't say where we're going to measure this from, so we're going to measure it from A to B. We're going to measure where Sam sits from A, and we'll need to finish that off in the answer as well. So that distance there, I am marking off as X. Okay, right, so we can quite clearly find out what M is by just resolving. I could take moments about there to save me having to do that. But now I've got, so if I took moments about this point here, then I wouldn't need to know this force, but it's dead easy. It's whatever these are added up. So I'm going to take moments about here, and it'll give me my distance X. So first of all, before I can do that, I need to formally tell the examiner that resolving upwards is positive. I'll be using net forces equals zero because it's in equilibrium. So to formally tell the examiner, the force M plus my 25G plus my 25G plus my 35G is equal to 0. So I've got, minus, they're going in the opposite directions, been a long day. M is equal to, that's 50, that's 85 G. Okay, and then at this stage here we can take moments. Moments about A, I'm going to do it. So clockwise is positive about A, and I've got the clockwise ones are that one and that one. So the first clockwise one is going to be 25G is the weight, and I'm multiplying it by 1.8 plus the other one is my 35G, and I'm multiplying that by X. Okay, and then the minus the anti-clockwise one is my force M, which is my 85G, and that's multiplied by 2. And we know the sum of all those moments is equal to 0. Quite clearly, we don't have to worry about this one because it's right acting through the fulcrum. So I can see that every one of these is going to contain G, so I can get rid of G. Rearrange it to give me 35X is equal to 85 times 2 is going to be 170 when thrown over, positive, and this is going to be take away, and it is 25 times by 1.8. So I could do that in my head, but I'm not going to. It's been a long time. So there we go, 45. So take away 45. So my final answer is that x is equal to 40. Take that as 130. So it is 125 divided by 35. Going to be a nasty decimal. So I've got 125 divided by 35 is equal to, there it is, SD, we've got 3.57. So x is 3.57 meters, and you need to say where you've measured it from. So from A. Okay, so that's what we get as the answer for that question there. 3.57 meters from A. That's where Sam would have to sit to keep it in horizontal equilibrium. Okay, right. Next question. It says a rod AB is 3 meters long. So here we go. 3 meters long, and that is A to B. It says and has weight of 20 newtons. So there's no need for G. It is in a horizontal position, resting on supports at C and D, where AC is 1 meter. So 1 meter, I've got a support there. So it's pushing it upwards there. That is C, and that is 1 meter. A to D is 2.5. So there is D, and that's 2.5, which means that's 1.5 there, and 0.5 there. I might have to worry about some of these in a bit. So that's yep. The magnitude of the reaction at C is 3 times that at is 3 times the magnitude of the reaction at D. So if I call D X and call the D down here and the C there, then this would be 3x. Okay, find the distance. 3 times that. Find the distance of the center of mass of the rod from A. So it's, I'm just doesn't matter where you put it. I can even put it here, even if I want to be stupid. But yeah, it doesn't matter where you put it. So I'm going to put it here, and that is a mass of 20 newtons. So it is just 20. And I know that this distance here, because we've used x, then this distance here I'm going to call y. Okay, right. So I can resolve vertically for a start to find out what x is. So resolve vertically using net forces equals 0, and I end up with basically 3x plus x minus 20 is equal to 0. Therefore x is equal to 20 divided by 4 is 5 newtons. Well, no, it's going to be just 5. Okay, right. So, well, it doesn't. Yeah, newtons. Okay, right. So anyway, I've got that. So this is going to be 15 newtons. This is going to be 5 newtons. So all I'm going to do now is, because we're measuring it from A, so because we're doing it from A, then I'm going to take moments about A, because I've got all the other information. So taking moments around A. I suppose we ought to start writing some of the force times distance is equal to 0. I suppose we ought to start writing that, so the examiner what we're doing and what this all means. I keep on forgetting that. Right, so here we go. We've got the first clockwise, and the only clockwise is this one here. So the 20 multiplied by this distance here, which is y. The others are negative moments, so negative, this one here is 3 times 5 is 15, multiplied by its distance is 1, and this is also an anti-clockwise, negative, so it is 5 newtons multiplied by its distance, which is 2.5. And we know the sum of those moments, as we say here, sum of these moments is equal to 0. Okay, so working this out, then I've got 20y is equal to 15 plus, and 5 lots of 2 is 10, half of that is going to be 12.5. okay, so y is simply going to be 27.5 divided by 20 as a distance, that'll be in meters. So calculator out, we've got 27.5 divided by 20, and that equals that, which is 1.375, and 1.375 newtons, meters. Okay, so we've got the distance there. That has to be somewhere around there to make this 3 times as the force, the reactional force as this one here. Okay, so that's the technique for doing these questions. If you've got any problems answering these questions in this exercise just here, then email me and I'll do a video of them. Okay.